Right, we want to talk about the Transformers project, and it's really supposed to talk about step-up, step-down transformers, buck-boost transformers, auto transformers, single-phase and polyphase transformers, current transformers, incident transformers, control transformers, which we've talked about a little bit already, and the kick test, which is about transform polarity. Okay? And as I was just saying moments ago, we're going to change this project, hopefully to add some new requirements to make it worth more points. Okay, I want to talk about step-up, step-down transformers. Here you see a pole-mounted transformer, and it's a step-down transformer. This one is a distribution panel with a transformer with a center tap on the secondary, and that's generally grounded to create what's called split phase power or an Edison 3-wire supply. And that should sound familiar from the project we did first. So this is how they create that. And you'll notice how many wires are on this thing on the primary side. See the wires running across the pole? How many wires do you see? 2, that's correct. You have 2 phases. You only have 2 hot phases. How are they getting split phase 120, 240 out of that? They're creating a ground and grounding the center tap of the transformers to create a neutral conductor, a grounded conductor in between the 2 hot conductors that are related to both. And so that's our basis for our Edison 3-wire. Buck boost transformers are generally used for special purpose. They're still step up, step down, sort of. They're not. Because a step up or a step down is where you're changing the voltage a lot. You're going from 480, 277, 480 down to 120, 208, which is like a 2-to-1 ratio, or a 4-to-1 ratio, or a 10-to-1 ratio, something like that. You're stepping up or down a lot with a step up or step down. With a buck boost, you are making a very minimal change. Okay? And they're not used a lot of places, but they are used to trim the voltage to what the equipment needs. A lot of tanning beds that we have here in the United States came from Europe, which is a different frequency of power and a different voltage. And so sometimes we need a buck boost transformer to change the voltage to the exact needed voltage. So this is a small transformer. This is a buck boost transformer. You notice it has 4 taps on the top and 4 taps on the bottom. And so we can get different voltages with different wiring setups. Okay, let's talk about auto transformers. And an auto transformer is where we've talked in the AC lab, if you're in the AC lab, the AC lecture class, about isolation transformers in the past, where we had a primary winding and a secondary winding, which is the most basic type transformer, and the windings are isolated. Well, here, this auto transformer is a transformer where the windings are connected. So you might only have 3 terminations because 2 of the windings are connected someplace. So it's not isolated mechanically or electrically. There's an electrical and a mechanical connection between the primary and the secondary, and that makes a lot of difference. Places where you will see in your future an auto transformer is at, for instance, the runway lights at an airport, or the taxiway lights at an airport. They're supplied by a constant current transformer. How do they keep the current constant? With an auto transformer, and it's got a floating coil to make everything stay the same. Why is that? Because we want the same exact brightness from them all the time. So what happens with those is if you run over one of the lights, it's got a built-in device that if you break the light by running over it with an aircraft, that it shorts the 2 connections together so the circuit stays on. And I can't think of what that device is called at the moment, but That's neither here nor there. Okay, so an autotransformer is a device where the two windings are tied together somewhere. Okay, single phase and polyphase transformers. We're going to study these in the AC class, and we're going to talk about them here in class also. Single phase transformers is where you just have a single phase coming in and a single phase going out. And polyphase transformers can be a single set of transformers that are built for three-phase in and three-phase out, or we can create what's called a three-phase bank, like our drawing here on the right where we have three poles on the right. Those are all three single-phase transformers, but they formed a three-phase bank. And they're connected different methods, and we'll talk about the method three-phase connections later. But what happens is, well, we'll talk about that later. We'll talk about connecting three single-phase transformers into a three-phase bank, because that is a project we're going to do, and I'll talk about that separately. Okay, current transformers, you've learned about them in the first semester, I hope. A current transformer is just a donut, so to speak, of wires that are wound very tightly. You run a single wire through it, and it infers the current in that by stepping that current down so that you can read it more safely. And what do we never do with a current transformer? Leave it open. Don't leave it disconnected and have current going through the wire that's going down through the middle of the donut, because you're going to be building up voltage potential and current potential, so that when you do touch them, you might get a really bad surprise. So it's one of the things we don't do with a current transformer is disconnect it. What can you do to avoid that situation? What happens in the loops of a squirrel cage motor? A short circuit. It's just running around in a circle, right? But it's a harmless circle. So we can short this circuit closed, and it becomes a harmless circuit. It's just running around in through the windings of the transformer. That's not hurt anything, and it's not building up voltage. Instrument transformers. I guess we're not going to talk about that today. I haven't prepared that slide. My apologies. We'll do that some other day. And control transformers. We have talked about control transformers in our theory class. And if you haven't heard that lecture, I would look that up and listen to it. But the thing that you need to know about this is it's designed to operate on two different primary voltages, depending on how you hook it up, and always put out 120 volts. That's what a control transformer does. Okay? A lot of across-the-line starters have a control transformer because it's one of the safer ways to supply the control circuit power. If you're using an outside lighting circuit for your control circuits, it presents a danger because you might have your power off and think all your power is dead, but you might have a control circuit that's live, so that's not so good. Common control is where you have line voltage from your primaries going through your control circuit. That might be 277, 480. Probably not a good thing to have on your contacts and touch the contacts and get 277, 480 across your fingers. It might be not a good thing. So control transformers are in most control setups and is, in my opinion, one of the best ways to do that. And finally, we need to talk about the kick test. This is the thing we need to talk about the most because this is the transformer polarity test that is the existing part of the project that you would do, or one of the parts that you would do already according to the current project handout. So what you're going to do is you're going to connect a battery to the primary side of the transformer, and then you're going to reuse a meter, an analog meter only. Anytime you see VOM in this lab manual, they usually mean volt ohm milliamp meter, and what they really mean is a Simpson 260 or some other good accurate analog meter. So you need to use an analog meter to do this project. You see it says VOM down at the bottom? Now, let me ask you a question. What voltage would you see if you have a 9-volt battery on the top? And let's just say that it's a 2-to-1 step-up transformer. Let's say it's a 2-to-1 step-up transformer. What would you see across the VOM in voltage? Very, very, very briefly, 18 volts. But for general purposes, after, let's say, a thousandth of a second, what will it say after that? 0. It will say 0 because, remember, DC, which is batteries, does not transform. It's going to step it up when you connect it. It's going to step it up when you disconnect it. But in between, it's not going to transform anything. There won't be any voltage across the secondary winding after a split second. In the lab final that you're going to take someday for this class, it's going to show you this diagram and ask you what is the voltage across the meter. If it's a 2-to-1 step up, what is the voltage? Trick question, huh? You got to remember that DC doesn't transform. Okay? What else? Read the lab manual and it will explain how the exact meaning of a positive kick or a negative kick, and it will show you transformer polarity from top to bottom. In other words, its own internal polarity, whether it's, you know what, I do need to draw something. So, let's see if I can get a new slide. Yes, I can. Let's take it, make it blank. Layout. Blank. Thank you. Okay, so let's say we have a transformer. Nice, simple transformer. And what we're looking for in this thing is if we're calling this positive, and we're going to, that means that the current is going across this way in time, in relation to time, right? Because if we pick a point, it'll either be going to the right or the left, right? But we're going to say at time 0, that first wave is going to go up. During that same time, what is the current going to be doing down here? If they're wound the same way, the current on the bottom is going to go this way. It's going to be in the opposite polarity of the induced current, right? That's what Fleming said. Fleming's left-hand rule says the induced current is opposite in polarity to the current that induces it. All right, so this is what we're talking about. So if we were looking at this, which one of these is positive? Right, exactly. So this one's negative, this one's negative. And that's the polarity we're talking about. Now, if this winding is opposite in polarity to this top winding, it'll be the exact opposite down here on the bottom, right? That's what that kick test is all about. Which way are these two wound? Are they wound going the same way, going opposite ways? Because they can be wound either way, right? And they are wound different ways sometimes. Okay, that's it for this one. Thank you for your patience, and I'll see you guys in lab.